The remote week on the course. This week you're going to be engaging with all lecture materials online via Moodle, so we have no in-person lectures. And what we will have this week is a series of much shorter lectures where we divide different radiometric techniques up into smaller bite-sized components. This is based on past feedback. People find this material a little bit hard to engage with a lot of content, so I've decided to split it up into more digestible bits. So if you remember, in our previous lecture we had talked about elemental techniques that are commonly used by radiochemists. Therein we looked at ICP AES, atomic emission spectroscopy, and then we followed that up with a derivation where we were still using the ICP, the inductively coupled plasma, but now it was hooked up to a mass spectrometer, and we saw some specific use cases where those two machines could be used by radiochemists. This week we're now moving on to solely discuss different radiometric techniques. So here we're using the properties of radioactive decay to tell which radionuclides are in a sample, and also how many or what concentration they're present in. So if you remember, in our previous lecture we had talked about elemental techniques that are commonly used by radiochemists. Therein we looked at ICP AES, atomic emission spectroscopy, and then we followed that up with a derivation where we were still using the ICP, the inductively coupled plasma, but now it was hooked up to a mass spectrometer, and we saw some specific use cases where those two machines could be used by radiochemists. This week we're now moving on to solely discuss different radiometric techniques. So here we're using the properties of radioactive decay to tell which radionuclides are in a sample, and also how many or what concentration they're present in. Now, as I say, we divide this up into bite-sized chunks. So in this first mini lecture, which lasts about 30 minutes, we're going to see general information pertinent to radiometric techniques. And the content that is presented in this lecture is very important, so please do make an effort to revise this thoroughly. After you've watched this short video on the general information, then you're going to move through the different other small video lectures. First go to gamma spectrometry, then move to a lecture that addresses both liquid scintillation and alpha spectrometry, and then in the final bite-sized lecture you'll learn about other detectors which are commonly used in the lab, as well as a radiation imaging technique known as autoradiography. So we're going to start with some basic information on radiometric measurements. And what you're going to see is that radiometric measurements are methods that are based upon the detection or measurement of radiation that comes from the decay of an unstable nuclide. And here what we're generally going to be doing is either detecting the particle types that are emitted from that radioactive decay, i.e. the alpha or the beta, or alternatively we will be detecting this EMR, electromagnetic radiation. And we're going to detect either of these things when they have an interaction with the material that the detector is made out of. We'll see that radiometric methods also take advantage of two types of interaction process when either the particle or the electromagnetic radiation impacts the detector material. So here those interactions that we're relying upon is ionization, so liberation of an electron, or excitation. Now in both of those cases, to be able to make a measurement, we're going to need to have an electrical signal being created from that interaction. And if we can capture that electrical signal, then we have a chance of being able to tell that the radioactive decay has happened, and also the identity of the parent isotope that has underwent that decay. Now, for situations where we're detecting ionization, what we're going to be doing there is collecting and amplifying electrons that are released from the ionization events, and then that will allow us to create an electrical pulse. Then with excitation, now we're collecting the photons that are being given off during the de-excitation process that has happened after the excitation. And again, from this, we're going to create an electrical pulse. And what you'll see is that the pulse rate for both of these types of detection is going to be proportional to the rate of decay. Further, the pulse height, again from both, is going to be able to give us information pertinent to the energy. And that's very important because if we can quantify the energy, then we have a good chance of being able to identify the radioactive decay that's just occurred, i.e. characterize the parent radionuclide that underwent the decay. So we're going to start with some basic information on radiometric measurements. And what you're going to see is that radiometric measurements are methods that are based upon the detection or measurement of radiation that comes from the decay of an unstable nuclide. And here what we're generally going to be doing is either detecting the particle types that are emitted from that radioactive decay, i.e. the alpha or the beta, or alternatively we will be detecting this EMR, electromagnetic radiation. And we're going to detect either of these things when they have an interaction with the material that the detector is made out of. We'll see that radiometric methods also take advantage of two types of interaction process when either the particle or the electromagnetic radiation impacts the detector material. So here those interactions that we're relying upon is ionization, so liberation of an electron, or excitation. Now in both of those cases, to be able to make a measurement, we're going to need to have an electrical signal being created from that interaction. And if we can capture that electrical signal, then we have a chance of being able to tell that the radioactive decay has happened, and also the identity of the parent isotope that has underwent that decay. Now, for situations where we're detecting ionization, what we're going to be doing there is collecting and amplifying electrons that are released from the ionization events, and then that will allow us to create an electrical pulse. Then with excitation, now we're collecting the photons that are being given off during the de-excitation process that has happened after the excitation. And again, from this, we're going to create an electrical pulse. And what you'll see is that the pulse rate for both of these types of detection is going to be proportional to the rate of decay. Further, the pulse height, again from both, is going to be able to give us information pertinent to the energy. And that's very important because if we can quantify the energy, then we have a good chance of being able to identify the radioactive decay that's just occurred, i.e. characterize the parent radionuclide that underwent the decay.
Now, we have two key modes for making radiometric measurements. We're going to have one set of techniques that are basically trying to count the pulses that are coming. And then we're going to have another type of technique where we're looking at energy spectrometry. So for pulse counting, all of the interactions that result from the particles or rays are going to be detected. And they're going to be detected as electrical signals, electrical pulses effectively. And we're simply going to be counting them, and we can be doing bulk counts across an entire energy range that a spectrometer can count across, or we can count those in selected energy ranges that we set before we start to make our measurements. Conversely, in energy spectrometry, the energy of the pulses are the thing that we're also interested in recording. And what we do when we're doing energy spectrometry is we collect the number of pulses and we sort them across into a number of channels. And those channels represent different wavelengths, different energies that the gamma radiation has come in and interacted with the detector at. And the number of pulses per channel is going to give us the ability to create and record what we call an energy spectrum. So effectively, the number of pulses against an energy.
So that's the different types or modes of detector that we can have. Now what we have here is a slide that's going to talk about the different components that we have in radiometric detection devices. And this slide's really here just to help a little bit. In the coming 2 lectures that follow here, we're going to be looking at different radiometric techniques, and this just gives you a bit of information on the different parts of that analytical equipment. So first up we have our detector, and that's going to be the actual part of the machine where we're going to be having an interaction between a radioactive decay, so radioactive emission effectively, and the actual detector. And we could have a direct interaction there, so that would be when we have emission of, say, an alpha or beta particle or some electromagnetic radiation interacting directly with the detector. And that would be when we have something like a gas ionization detector or a semiconductor detector. And we'll talk about both of those in the following lectures. Or we could have an indirect interaction. So here we would have the radioactive decay giving some energy to another material, and then that material would emit some light after absorbing that energy, and then light would be detected. And that's when we have scintillation style detectors, and we'll look at both solid and liquid scintillation detectors in this course. Next up we have information on the preamplifier and main amplifier, and this is commonly in semiconductor detectors. So our preamplifier is going to take this initial weak electrical pulse that we get from the interaction between the radioactive decay and the detector material, and then that is going to enable the transfer of that electrical pulse into the main amplifier. And then our main amplifier, also called a linear amplifier's job, is basically to increase the pulse height into something that's more measurable, whilst also preserving information on the energy of the decay that has just been detected. Then in scintillators, we often have this photomultiplier tube. So what this is going to do is convert energy from the photon that's just come from the interaction of the radiation with another material, and it's going to convert that photon into an electrical pulse. And then we can have that amplified into a measurable electronic signal within the photomultiplier tube, and we'll show you how that works in later lectures. Then we have this SCA and MCA, so single and multi-channel analyzers. In the single channel analyzer, we're counting pulses across a defined energy range, and this is good for when we just have a single radionuclide in a sample and we need to measure its overall radioactivity. However, if we have multiple radionuclides in our sample, then we need to make use of an MCA. So this sorts our pulses into various channels depending upon the height of the pulse. So effectively we're getting here a measurement that's proportional to the energy of the particulate radiation or the electromagnetic radiation that is being detected. And this allows us then to effectively have different decays at different energies displayed in the same data set, which allows us to look not only at the amount of radioactivity in the sample, but specifically the amount of radioactivity at different energies, and therefore we can sort that out into different decays from different radionuclides.
Okay, before we move on to look at techniques specific for measuring gamma decay, I want to talk about something that is uniform across all of the detector types that we're going to be looking at in the next couple of lectures, and that has to do with how we quantify the amount of radioactive decay, and that's done via the pulse rate or the count rate. And it's important that we talk about this because there's a great number of factors that affect the pulse rate, and they have big ramifications on the sanctity of the data that we're trying to collect, so its precision and its accuracy. So when we're doing pulse rate counting, we're essentially taking electrical pulses from the primary interactions between the radiation and the detector material. And that could be electrons that we're basically trying to collect an electronic signal from, or it could be photons that we then convert into an electronic signal. And we collect that information per unit time, and the pulse rate or the count rate is going to be directly proportional to the sample's rate of radioactive decay. So the pulse rate tells us about the activity of the radionuclides in a sample, or the radionuclide in a sample if it's a very simple substrate that we're measuring. But what we're going to find is that the counting efficiency, E, of a radiometric detector, amongst other factors, has to really be considered with some care. Now the count rate, which we express as counts per second or becquerels, is going to be the product of the activity of the sample times the counting efficiency of our detector. And E is something that we're actually going to have to try and correct for in our detector, because the efficiency of most radiometric technique detectors is not very good. And we're going to account for changes in efficiency with different types of detectors, and also changes in efficiency between different types of sample via use of a number of different coefficients. This is the equation that we have below. So we have efficiency equal to 6 different coefficients that we're going to learn about on the coming slide. And this is all very important information for a radiochemist. So whilst there's a lot of text on the slides that come up, this is something that you do need to commit to your memory. Quite possible that I will ask you a question about how you deal with correcting for efficiency in radiometric measurement.
Okay, so first up we have the sensitivity coefficient, C subscript SE. This coefficient represents the amount of radiation that comes into the detector that actually has a chance of being transformed into a measurable electrical pulse. And that can be for particle types of radiation, so alpha or beta, and also electromagnetic radiation, so gamma. Now, this sensitivity coefficient we will find is going to depend upon the type of material that the detector is made from, and also the type of radiation that is impacting the detector. You're going to find that all detecting materials are essentially more sensitive to alpha and beta radiation than they are to incoming gamma radiation. And that's because gamma radiation in its electromagnetic form with very, very high energy and very, very short wavelength is going to be able to come in but actually pass through the detector without being scattered or any of its energy being absorbed. Indeed, often only a very small percentage of gammas actually deposit information in the detector such that it could lead to their quantification. In contrast, quite a large proportion of alpha or beta particles that are entering a detector can be absorbed, and therefore we can be able to create quite easily an electrical pulse from them in the detector. So we deal with this variance essentially using this sensitivity coefficient.
The next thing that we have to consider with regards to the pulse rate and that we have to make a correction for is the geometry of the sample relative to the radiation detector. And we take care of this by considering the geometry coefficient, or C subscript GE for short. Now, the geometry coefficient is relevant for all types of radiation, and it's relevant in exactly the same manner. Now, when we have a radioactive decay event, we're either going to have particles or rays being emitted randomly in all directions from the sample. But it's only those particles or rays that hit the detector that actually have a chance of being detected and forming an electrical pulse. Now, I've given you a simple example here in the bottom right hand of the slide. Here we're considering a radioactive point source sample, which is at a distance of h from a round cylindrical shaped detector that has a diameter of r, and only those particles or rays that are being emitted from this point source that have a space angle of g are going to be the ones that are actually able to be detected. And in this example, we can account for the geometry using this equation that you see at the bottom of the slide. And if we have different types of samples and different types of detector, then we can have different equations that allow us to come up with this geometry coefficient. Now, I don't need you to learn those equations. You'll be glad to know, and I don't need you to do any calculations with them. I just need you to be aware that geometry is something very important that we need to take care of. I also want you to note that quite often we don't have point sources in our lab. In fact, I pretty much never have measured anything that I consider to be a point source. So geometry is something that can be actually quite hard for us to be able to take care of and correct for in our measurement. Now, one thing that we can do, especially in gamma spectrometry, is we can have detectors that are shaped like a cup. We call those well-shaped detectors, so they're not planar like the example detector, the cylinder detector that we have in the diagram. When we have a well detector, we can put our sample inside the well, and that gives us a greater way of getting the radioactive emissions into the detector material, and that increases the likelihood that we have them being detected. So that takes care of some of the geometry problems that we would have, for instance, if we just put a sample on top of a cylinder type detector. Also, we don't have to worry about geometry when we're measuring things via liquid scintillation. That's a technique that we're going to be looking at in the next lecture about radiometric techniques. And here, because we put the sample in a liquid, we don't have any geometry considerations that we have to worry about. The next thing that we have to consider for correcting our pulse rate is the dead time. And we do this by the dead time coefficient C subscript dt. Now, the dead time is the time when the detector is unable to process a new pulse because it is still processing the last pulse that it received. Thus, the dead time is the minimum time that the detector needs to separate two radiation events, and thus for them to be recorded as two separate electrical pulses. Now, we can correct or come up with our correction function for the dead time using the equation that you see on this slide. So here R is the observed count rate, tau is the dead time, and R0 is the count rate that is being corrected for the dead time. Now, the dead time gets higher when we have more activity in our sample, and we can visualize this quite well in this figure that I've taken from the Kratz and Leisner textbook, Nuclear and Radiochemistry, published by Wiley. And here you can see our counting rate on the y-axis expressed in units of counts per minute, and then on the x-axis we have the number of pulses that aren't being counted, also expressed in CPM. And basically what I want you to take away from this diagram is that as the count rate goes up, the detector is struggling more and more because it has this dead time. And so as we have increased count rates, the number of non-counted pulses goes up vastly. And you can see that at some spaces when we get into very high count rates, we're missing about 10% of the overall counts that are coming into the detector. So this is actually something that is quite significant, especially when we have highly radioactive samples in our detectors. We have to be sure that we're applying corrections for dead time. The next thing that we need to take care of is the backscattering coefficient, which is C subscript BC. And this is really of primary relevance for beta particle counting and quantification. So essentially here we're worried about beta particles scattering from other atoms in the materials that surround the detector. So it really should only be the beta particles that are in the direct line of sight of the detector that are being detected. However, beta particles, particularly high energy beta particles that have not initially been emitted in a direction that would take them into the detector, can actually impact and scatter off surrounding materials, such as the lead shields that are quite often used to shield the detectors from the background radiation that we would have in a laboratory. And so the effect of the background scattering is that it can actually increase the observed count rate that we would have in the detector to make it higher than the true value. Now, backscattering is dependent upon the materials that we have in our detector setup. So if we have shielding materials that are made of a particularly high atomic number, for instance, then it can more efficiently backscatter those high energy betas and potentially direct them back towards the detector, giving us a false high measurement. Also, the situation, the geometry of our detector can increase the amount of backscattering. So particularly if we have our shielding materials quite close into the detector, then we're going to increase the chances of having backscattering events, putting those beta particles into the detector. Now, backscattering is something that I've said is primarily of concern for high energy betas, but it's not something that we're worried about if we're quantifying that beta radiation via liquid scintillation counting, and we'll talk more about that in the next lecture. For gamma radiation, and particularly for alpha radiation, backscattering is not something that we really need to worry about and make corrections for in their measurement. The next thing that we need to take account for with regards to pulse rate and its correction is the absorption coefficient, which is C subscript AB. This accounts for the absorption of radiation between the sample that is emitting the radiation and the detector. And this depends upon the type of radiation that's being emitted from the sample and the material that fills the void between the sample and detector, and then also the distance between the sample and the detector. Now, absorption is most relevant for alpha radiation because, of course, alpha particles have a very short range and they can be effectively absorbed even by air if that's what's filling the space between the sample and the detector. And because of that, as we'll see in a later lecture, alpha measurements are usually done in a vacuum because that really cuts down the chances of the alpha particles being absorbed before they actually impact the detector materials. Then when we're considering absorption, it's not something that we really need to worry about very much for gamma radiation because that is indeed of high energy and is therefore quite penetrating, and it's not really going to be troubled much, say for instance by an air gap between the sample and the detector. With regards to beta particles, well, yes, if we're doing things like liquid scintillation counting, which is something that we'll learn about in a later lecture, we can have some of the beta particle energy being absorbed by the solvent in our scintillation fluid, and therefore that can affect our measurements, and we'll see how we can account for that in later lectures. Also in gas ionization chambers, which is something that we're going to look at for the measurement of alpha and beta particles, we can have some absorption effects when we're trying to get those particulate types of radiation into the detector. And again, that's something that we'll look at in a little bit more detail in a later lecture. The next thing that we have to think about is the self-absorption coefficient, which is C subscript SA. This deals with the radiation that's absorbed by the sample itself after a radioactive decay event occurs within the sample. So again, just like the absorption coefficient that we spoke about a minute ago, this is going to be most important for alpha decay because it is the one that's most easily absorbed, and it's going to be least important, of course, for gamma decay. Now, self-absorption is dependent upon many factors, so that's looking at the elemental composition, the density and the thickness of the samples. Those are all very, very important, and we can have very special considerations that need to be made for alpha emitting samples. So you will see in a later lecture how we can get around some of these impacts of self-absorption, doing things like electrodeposition of alpha particles onto metal plates that we use, that we put right up to the alpha detector to stop self-absorption being a problem. We can also do things like microprecipitation and liquid scintillation counting for alpha particles to try and get around self-absorption. And this is just a diagram where I want to demonstrate to you the effects of self-absorption. This is for beta radiation that's coming from the decay of calcium-45. And this is calcium-45 that's in a matrix of calcium carbonate or calcite. And I just want you to see that self-absorption here is expressed on the y-axis, ranging from 0 to 1. So from 0% to 100% being absorbed in the y-axis. And you can just see how self-absorption varies across the thickness of the sample. And so when we have reasonably thick samples, we can assume that the beta particles aren't actually going to be able to get out of the center of that particle, out of that sample, and be able to get into our detector for the interaction to occur that would allow us to make quantification. So accounting for self-absorption is something that's really important for our samples, and we take great care in trying to correct for this when we're working with our detection techniques in a radiochemistry lab. On this slide, I'm just discussing some of the things that we can do to try and address some of these factors that would impact our counting efficiency. Now, one could try and address all of the aforementioned factors for every sample every time we want to make a measurement, but that's far from ideal. Our lives would be consumed by trying to take account of these different things for every different sample. It's just not practical for us to do that. So instead, one of the things that we can do that takes care of many of the factors that we have just outlined, is to prepare like samples together. So samples that have the same chemical composition, the same radionuclides in them, the same size, same density, and then we make them all up in the same geometry. And then what we try to do is match those to a standard that also falls in terms of the same chemistry, same density, same size, same geometry. But in that standard, we put a known amount of the radionuclides that we're trying to measure. And then if we have that standard and we measure everything underneath the same conditions, the activity of the unknown can then be calculated relative to our standard using the below equation. And that allows us to rule out having to think too much about all of these different factors that affect efficiency. And so in that equation, we have AX, which is the activity of the unknown sample, RX is its count rate, RST is the count rate of our standard, and AST is the known activity of our standard. And we can either make those standard samples up in our lab, or we can actually buy them in from companies that manufacture them, and they come with a standard certificate that tells us about the radioactivity that was in them at the point when they were made, and we can use decay corrections to the point when we make the analysis to be able to use this equation for our samples that are unknown that we're trying to measure. Also, just to highlight to you that when we're measuring aqueous samples and we're doing gamma spectrometry, it's enough that the samples are being measured in the same geometry. So they have to have the same size and they have to have the same distance and alignment to the detector. But because the gamma radiation is quite penetrating, we don't have to worry about a bunch of the other things in terms of absorption between the detector and the sample, and also self-absorption in our sample, because the gamma rays can quite easily get out of that. And then the final thing I want to say before we move on to start to talk today about gamma spectrometry is that there's also a range of computational approaches that can be applied to try and take care of some of these factors that impact the efficiency of getting an accurate count rate from our sample. However, I'm not a great fan of those computational approaches. I don't really use them in my analysis. I prefer more hands-on approaches to try and match a standard to my samples. And so I don't really teach about those computational approaches on this basic course. but it is something that we do look at a bit more in our analysis courses and our advanced nuclear spectrometry course that form part of our master's program.
Okay, so that takes us to the end of this first mini lecture. The thing that I would do next is log into Moodle again, and you'll find there that there is a small pop quiz that's associated with this lecture. Carries no marks, but you can complete it and it will be automatically graded and give you some feedback on what your knowledge is with respect to what we've just seen in the lecture. Once you've reviewed this lecture material and taken that pop quiz, then the thing that I would suggest is that you move on to the mini lecture on gamma spectrometry. Thanks for listening.